Hey guys, this is CHEMPLIFIED and today we will talk about VAN'T HOFF factor. So let's start. Before we talk about VAN'T HOFF factor, there is a statement that you should remember for the future reference in this video. And that statement is, it has been observed that difference in observed and calculated molecular mass is due to association or dissociation of solute molecules. There, so it's simply saying that there is a difference between calculated and observed molecular mass in the solution of solute particles, right? And this results in change in number of particles in the solution. How this is happening? Let me just give a simple example. For example, you have a solute NaCl, right? Now, how many molecules are there of NaCl? Only one. But as soon as you dissolve it in the solvent and convert it into a solution, you will find that you have Na plus Cl minus in the solution. Now you provide with one molecule and you are getting two particles in place of it in the solution. So this is an example of dissociation. For association, you can consider this example. You have two nitrogen atoms which combine together to form N2 molecule. In the starting, you have two nitrogen atoms or two different particles which combine together to form a new particle, that is one in quantity. So in first case the quantity of particle is increasing, in second case the quantity of particle is decreasing or the number of particle is decreasing. This is what we are talking about in VAN'T HOFF factor. About dissociation or association we will talk separately in the upcoming part of the video. Now what is VAN'T HOFF factor? VAN'T HOFF factor tells us about the relation between normal colligative property and abnormal colligative property. In simple terms, we know that colligative properties depend upon the number of particles of solute. So we are talking about number of particle of solute in observed quantity and in calculated quantity. When you calculate, there is some abnormality, right? That is it. Sorry, it is about which we will talk in VAN'T HOFF factor. It is represented by the letter I, small I. Now look at the formula. Number of particles after dissociation or association upon number of particles before dissociation or association. Now look at our first example which we talked about, NaCl. In the starting we have one particle, right? Afterwards we have two particles. So number of particle after dissociation we have 2, upon number of particles before dissociation we have 1. So the value of I is equal to 2 in this case, right? Or you can also write it as observed colligative property upon calculated colligative property. A third formula is also there which states VAN'T HOFF factor is equal to calculated molecular mass upon observed molecular mass. Now let's move to the next part. Now remember, if I is equal to 1, if the value of I is equal to 1, neither dissociation nor association will occur. It means the particle will not divide. Example, glucose, urea, sugar, they dissolve in the solution but they do not make ions or they do not combine together to form a new particle. Second, if I is greater than 1, if I is greater than 1, it means dissociation will occur. You already know that when we calculated this part here, I value of I is 2. So in this case dissociation is occurring, right? Now if I is less than 1, association will occur. Now for dissociation, compounds are examples that you can take is NaCl, KCl, BaCl2. For association you can take CH3COH, PHCOH. Right, in benzene the solvent is benzene, right? So these are the example that you can remember. Now comes to the main part. Now comes to the main part, that is first part, dissociation of solute. Dissociation of solute. Now let's read the statement first. Molecules of electrolytes undergo ionization or dissociation in pure solvent to give two or more particles in the solution. This dissociation results in an increase in total number of particles. Yes, number of particles are increasing since, let us take the example of NaCl only. First we have only one component. After dissociation we have two different components, right? So number of particles in the solution will increase, right? And therefore the value of colligative property of such solutions will be higher. Why they will be higher? Because colligative properties are inversely related to molecular weight. The molecular weight of the ionizable solute will be less than the theoretical value. Or in other words, you can also say that colligative properties depend on number of particles of the solute, and since number of particles are increasing, the colligative properties will also have a higher value. Alright, so this is your dissociation of solute. Now, since the number of solute particles are increasing in the solution, observed colligative property will always be greater than calculated colligative property. If number of particles are increasing, observed colligative property will be greater than calculated colligative property. Observed or experimental molecular weight of solute will be less than calculated molecular weight of solute. Remember, colligative property is inversely proportional to molecular weight of solute. Now comes the calculation part for dissociation. Calculation of I for dissociation. Alright. So let the solute be AXBY. Right. Now the equation that we can make is AXBY gives XAY plus YBX minus. Right, where x plus y is number of ions. An electrolyte when dissolved in a solvent, it dissociates into ions, right? So x plus y represent the number of ions. Now initially what is the concentration? Let the concentration of the solute be 1 mole. We are taking 1 mole. So initially these two ions will have 0 moles in the solution. Now after some time, that is after dissociation, let us suppose alpha number of ions are dissociated. So how many ions are remaining? 1 minus alpha. How many ions are formed? X alpha and Y alpha. Right? In equilibrium we have done this. Now if you solve for total number of solute particles, now listen carefully what I am going to write. Total number of solute particles. Total number of solute particles. Look at the equation. 1 minus alpha plus X alpha plus Y alpha. Now the problem is why I am including this quantity. It is in the reactant side. For that you have to know what is alpha. Alpha is known as degree of dissociation. Alpha is degree of dissociation. How many particles are able to dissociate? How many solute particles are able to dissociate into ions? Right? Now we have put 1 mole completely in the solution, out of which alpha dissociated into ions, that is X alpha and Y alpha. The remaining is also present in the solution and will be considered as a solute. Even if it is not converted into ions, it is still present in the solution and will be considered as solute because AXBY is our solute. So that's why we have to consider 1 minus alpha in the equation. Now let's solve it. We get 1 minus alpha plus, take alpha common, x plus y. Now what is x plus y representing? X plus y representing total number of ions. So you can write in place of x plus y, you can write n alpha, n in place of x plus y. So how many moles of solute are there? 1 minus alpha plus n alpha, right? Now comes our colligative property. Now what is the value of I? I is equal to number of particle before, sorry, after dissociation upon number of particle before dissociation. Now before this and after dissociation we have this value, so we can write 1 minus alpha plus n alpha upon number of particles before dissociation. We have only one component, so our number of particle will be equal to 1. Why? Let me show you again. In the starting of the equation, we have only one component, only one molecule is there which is dissociating in different ions. If the quantity is 1 mole, the remaining will be 1 minus alpha, which we have to include in our total number of solute particles, right? Right now, therefore the value of I is directly written as 1 minus alpha plus n alpha, right? Now you can take alpha common. After taking common, you will get I is equal to 1 plus n minus 1 alpha, where alpha is degree of dissociation, and this is your formula to calculate I for in case of dissociation, right? Now for strong electrolyte like NaCl, strong electrolyte like NaCl or KCl, HCl, these are strong electrolyte. For them alpha is equal to 100%. For them alpha is equal to 100% or alpha is equal to 1. So in case of strong electrolyte, value of I will change as 1 minus n minus 1 alpha, and you know that alpha's value is 1. Alpha's value is 1. Substitute the value. Consider the example NaCl. For NaCl, after dissociation, number of ions will be 2. So n is equal to 2. Substitute all these values. You will get 1 minus 2 minus 1. Final answer for I is equal to wait a second. Yes, in this place plus will be there because in our main formula we have written plus. I have changed the sign by mistake. So the final value will be 1 plus 1 is equal to 2. So for NaCl, only for NaCl value will be equal to 2. For KCl and HCl also value will be equal to 2. Let's take some other example for which value is not equal to 2. Let us take the example of K2SO4. Now after dissociation it will give you 2K plus SO4 2 minus. So value of N will be 3 in this case. Alpha is 100% is equal to 1. Now put it in the formula. I is equal to 1 plus n minus 1 alpha. 1 plus, what is the value of n? It is 3 minus 1. Now alpha is also equal to 1. So the final answer will be I is equal to 3 for K2SO4. That's how you calculate I for the dissociation of solute, right? Now let's move ahead in our video. Now comes our association. Association of solute. Now what happens in association? The formation of bigger molecule by the union of 2, 3 or more solute molecules is called association. As a result, the total number of particles in the solution become less than the number of molecules initially dissolved in the solution, and hence colligative property will have a lower value. It is just opposite of that of dissociation. In case of dissociation, the particles were dissociating, increasing the number of particles. In case of association, the particles will combine together and will decrease the number of particles in the solution. Right? Now, since number of solute particles are decreasing in the solution, observed colligative property will be less than calculated colligative property, and observed molecular weight of solute will be greater than normal molecular weight of solute. Right? Remember this, and also remember this is just the same as the previous one. Colligative property is inversely proportional to the molecular weight of solute, and for association value of I is less than 1. These are just the statement that you have to remember. Now comes our main part, that is the calculation of I for association. Let us first consider our general equation. Na gives An. To understand this, just take this example. We have already used it in previous part of the video. Two nitrogen atoms combine together to give nitrogen molecule, right? So in case of 2, we have written N, and in this place you have written 2, right? So you can just relate with the equation. Now comes initially how many moles are there? 1, and for product 0. Now after what? After association, what is happening is 1 minus alpha and alpha upon n. Why n is in the division? Because the number of particles are decreasing. If the number of particles are increasing, you multiply alpha, and if the number of particles are decreasing, you divide alpha. Just if you have not read it, you can go for equilibrium, chapter equilibrium. In that you can understand this concept. Now let's move ahead. So the total number of solute particles will be equal to total number of solute particles will be equal to, now since even if all the particles are not associated together, it is still present in the solution. So you have to consider this in total number of solute particles. So the total number of solute particles will be 1 minus alpha plus alpha upon n, right? Now Van't Hoff factor value will be, Van't Hoff factor I is equal to number of particle after association upon number of particle before. Right, this is the formula. Now put the values. I will be equal to 1 minus alpha plus alpha upon n upon में 1, right? Now you can go for the question that in the starting we have taken the equation as like this. So there are n number of particles in the product, but we are not talking about n number of particles. 1 mole also represent what? Number of particles or molecules, right? So our starting material, let me show it to you again. Our starting material is how many moles? 1 mole. Out of 1 mole, the dissociation is happening or the association is happening. So how many particles are there? 1 mole. That's why in the denominator we are taking 1 mole. All right. Now let us consider our alpha value equal to 100%. Let us consider that for this association alpha is equal to 100%, which means all the particles are getting associated, which means alpha is equal to 1. If alpha is 100%, it means alpha is equal to 1. Now what is happening? Right, take a look. I will be equal to 1 minus 1 plus 1 upon n. So these two will become 0. So the value of I will be equal to 1 upon n. Right? You can consider another example. Let me move the screen first. Let us consider an example. Consider an example of CH3COH. 2CH3COOH gives CH3COH twice. Now initially we have 1 mole, right? 0 moles. After some time 1 minus alpha get associated and alpha by 2 are formed. Right? Now consider alpha is equal to 1 in this case. Now the value of n is also equal to 2. We have already found the value of n. Now substitute I is equal to 1 minus alpha plus alpha upon n. This will give you I is equal to 1 minus 1 plus 1 upon 2. These two will get cancelled out. Answer will be I is equal to 1 by 2. That's how you reach the value of I in case of association. Alright. So this was your association of solute, and we have already done dissociation of solute. This was your complete Van't Hoff factor and all the calculation part that you can use in this particular topic. So this will be it for today's video. Thank you for watching. Have a good day.